Great. Well, thank you very much, Chris, for the kind introduction. So I'm Ken Crozier. I'm from the University of Melbourne. And so I'll be speaking today about optical nanotweezers and mid-infrared chemical classifiers. So this is a picture of folks from the University of Melbourne TMOS node. So we have two chief investigators, Anne Roberts and me. And this is the picture of our groups, but also a few of our collaborators, the associate investigator Tas Nemolathis, as well as some of the collaborators from biosciences. So this slide shows a bit of a sampling of what we do in my group. We're working in the area of micro-optics and nano-optics. As shown in the upper left, we're very keen on new types of photodetectors based on nanophotonics and nanomaterials, 2D materials like graphene, like platinum diselenide, like black phosphorus, molybdenum disulfide. And this, for example, was showing, I guess, a platinum diselenide device and looking at the photoresponse at about 8 micron. We're also working on metasurface-based holograms, working on metasurface-enabled micro-spectrometers, and working on optical nanotweezers. And those bottom two there, the nanotweezers and the mid-infrared microspectrometers, that's what we'll be talking about today. So let's talk about the nanotweezers. Yeah, we're very keen on optical nanotweezers. So you might know that half the Nobel Prize in Physics in 2018 went to Arthur Ashkin for introducing optical tweezers. And so the problem statement is as follows. As we know, conventional mechanical tweezers are very useful for manipulating millimeter-sized objects, but how do we get this sort of functionality? In other words, holding something in place to observe it or to manipulate it in some way. How do we achieve that for micro to nanoscale objects? And so in Arthur Ashkin's approach, he showed that if we focus light with a lens to a small spot, then we can use the momentum carried by light in order to apply forces to objects over a very wide range of length scales. But as we move toward the nanoscale, toward trapping smaller and smaller particles, then conventional tweezers based on focusing light with lenses starts to run into some challenges. Oops. And we can understand that by looking at the expression for the force on the particle that's small compared to the wavelength. So if the particle is small compared to the wavelength, we can model it as an electric dipole, where the dipole moment is equal to its polarizability multiplied by the local electric field. And if that's the case, if the particle is small and it can be considered as a dipole, then the force on it in an electromagnetic field breaks down very neatly into 3 components. The first component is called the gradient force. And you can see why, because it's proportional to the gradient of the intensity. It's also proportional to the real part of the particle's polarizability, which is in turn proportional to volume. And in a conventional tweezer, what we want to do is we want to maximize that gradient force so the particle experiences a force that pulls it to the region of highest intensity. The other terms are the radiation pressure force and the spin curl force. And if we look further at that expression for the gradient force, then we'll see what the challenge is when going to the nanoscale. The gradient force is proportional to the volume of the particle. In other words, its radius to the 3rd power. So as we make that particle smaller and smaller, let's say we drop the radius 10 times, the force will drop on it 1,000 times. In other words, it's hard to trap those very small objects. And you may think, well, why can't we just increase the gradient of the intensity somehow? Well, that's because if in a conventional tweezer, we're subject to the diffraction limit that tells us that we can only focus light to a spot size of about half a wavelength, right? So for a given laser power, for a given particle, there's an upper limit on the force that we can exert with the gradient force with the conventional tweezer. However, with nanophotonics, we know that we can break the diffraction limit, right? We can concentrate light to spots that are smaller than the half wavelength limitation, and we can also make those spots more intense. And that's where ANFF facilities come in, right? Because it's how we're going to make those nanophotonic structures. And so, so that's been a topic that people have been quite interested in over the last dozen years or so. And so people have used these plasmonic nanostructures. So take a metal film, open up an aperture in it, a circular aperture, a rectangular aperture. This one here is called the double nanohole aperture, bow tie aperture, coaxial nano aperture. When you shine light into them, then the light is concentrated inside that gap region, concentrated region that's much smaller than the wavelength, and you can use that to trap particles. But there's also other effects in addition to the concentration. In other words, when the particle is trapped, that perturbs the resonance, and that can actually have a favorable effect on the trapping. It also enables you to monitor the trapping process very readily, because one can see these kind of sharp step-like transitions in the optical transmission through the aperture due to the presence of the particle inside that aperture changing the resonant nature. But what you see there is that if there's this wide variety of structures, right, that have been made using facilities similar to what we have in ANFF, right? But why such a wide variety of structures? Well, the way we look at it, generally speaking, the design process has been as follows. People choose some sort of a shape, right, largely driven by physical intuition. For example, this one here, this coaxial nano aperture, I think that's probably inspired by coaxial cable, right? And so they choose that, and then they vary the geometric parameters, like the inner and outer radii of those holes, in order to fine-tune it, and then find the structure that's best. So what we've been doing is we've been working on an alternate approach where rather than this intuition-based approach, we use a computer algorithm. And we use a method called the inverse design method based on the gradient adjoint method. And so what we're doing is we start off our simulation, if you will, with just some very simple structure. Here we have a pair of gold cylinders separated by a small gap. And so that black represents the permittivity of gold, and then that white represents the permittivity of water, because these are designed to operate in water. So that's the starting point. And then the surrounding region has a permittivity that's intermediate between that of gold and water. And so then what we do is, we start that off, and then we have a gradient-based approach where in each iteration of that algorithm, it's choosing the shape in order to increase the field enhancement at the very center of that structure. And so we start off just this very simple structure, 2 cylinders, and let's see what we get. So the process is running, the algorithm's choosing the permittivity at various points, and then it keeps on running, and then we were kind of a little bit staggered when we got this result, because this is very, very similar to this structure here, this double nanohole structure that was introduced by Reuven Gordon's group in Canada, and is being used by about 5 different groups around the world. And it was kind of this physical intuition-based approach, but our algorithms come up with that type of structure. Once we've designed that nano aperture, then we design the surrounding region. So we think of this as like a coupler to couple electromagnetic waves into that aperture. And so again, we use this gradient adjoint method and let it run. And so we keep this area in the center kind of open like that. And so it's running, so it's choosing the structure here. And so we refer to this as our the structure that it comes up with. What does it look like? Okay, what would you think this looks like? So we kind of jokingly refer to this as our nano Rorschach test, because it kind of bears a lot of similarity to Rorschach tests. And then at the end, and then once we've done that, then we put the nano aperture in the center and have the combined structure. So when we look at the performance there, then what we find is we look at the field enhancement. In our structure, it's about 64 times. Our previous inverse design method got up to about 44 times, whereas that double nanohole, which is the structure that was kind of the popular one, done by about 5 different groups, introduced by Reuven Gordon's group, it's getting up to about 12 times. So in other words, about 5 times greater electric field enhancement. And so that means that the intensity enhancement is about 25 times greater, or even a bit more than that. And that leads to, so they've got more than an order of magnitude increase in the trapping force that you get from this inverse design method. This has been fabricated by Anders Barlow, who's in the audience down there, at the MCFP at the University of Melbourne. And so the inner structure has been made by the helium fib, the outer structure is made by the neon fib, and so this is all made in 100 nanometers of gold on glass, and I believe Anders will be presenting some of this in a poster, I believe, at ICON, so look out for that one. Now, I promised 2 topics. I said nanotweezers and chemical identifiers. So I'm not going to talk in a lot of detail here, but you know, one of those things that I mentioned, one of those other topics I mentioned in my title slide was we're very keen to make miniature infrared spectrometers, right? So the idea is, can we have the same sort of functionality as the FTIR spectrometer, right? And so, you know, we have an FTIR spectrometer, Fourier transform infrared spectrometer in our lab. Weighs about 50 kilograms, takes up several feet of lab space. That 50 kilograms doesn't include the computer, so you add a bit more to it on that. But can we get something that weighs, you know, like a gram, right? And can it be something as big as a cube of sugar? Can we do that? And can we get mid-infrared spectroscopy good enough to identify chemicals? And so we've done that. We've made use of the Melbourne Centre for Nanofabrication. And so we've got 2 steps. First step, we make our filter chip. So it's very simple. Lithography, evaporation, liftoff. That's it. You've got your filter chip. And then we take this miniature thermal camera from FLIR, the FLIR Lepton. We take it apart very carefully. Involves the use of a razor blade here. And then we bond our chip onto the sensor array, where the different filters are kind of lined up with different pixels on that center, and then we put it all back together again, okay? And there's another picture there, kind of of it all assembled. And so the idea is we have infrared light, it's going through some analyte, then going into our micro-spectrometer, and then each of those filters, there's a bunch of different filters there, about 20 different filters. Each of them is either transmitting or not transmitting light to a sequence of detectors underneath. So we made that, and then we've gone and trained it up by machine learning. So what we do is we take that system there, and then we subject it to different chemicals at different concentrations, right? Put the chemical in there, read it out. Put a different chemical in there, read it out, and so forth. And then we go back and then we go and do a series of tests where we just give it some chemical and ask it to identify it. And so in the first one there, then what we see is these the tests of common chemicals: isopropanol, acetone, ethanol, ethyl lactate. True class in the rows, predicted class in the columns. What you see is it's all completely along the diagonal. It's 100% accuracy in identifying those chemicals. Here we show the predicted versus actual concentrations of ethyl lactate. Again, lying along the, you know, it's lying along this line here. Whoops, sorry, I realised. It's lying along the line there, right? So very close to that line. Here we've used it to identify different medications: aspirin, ibuprofen, paracetamol. Again, along the diagonal. But then here we've kind of ventured into the kitchen and then looked at olive oil versus peanut oil versus vegetable oil. Again, very highly accurate, except for peanut oil. It's sometimes misclassified as olive oil. So we've also extended this. We're using it for gas detection. And I can see the chair of the session's rising. So I'll just summarize. And then most important thing, fabrication was performed at the MCN, and it was supported in part by the MCN Technology Fellow Ambassador Program. Thanks very much for your attention. That concludes my presentation.
Thank you very much, Ken. Are there any questions? We've got time for perhaps one question before we go on to the next speaker. Yes, there's a question.
How did you actually align your filter array with the bolometer array? Is that correct?
Yes, that's right.
How difficult was that?
So it's not so difficult because, I mean, the filters are roughly about, I think maybe 150 micron by 150 micron. So we actually used there's a flip chip bonder in at Melbourne Uni, which we used for that, but that was just for the alignment. But then there was one day where my students and postdocs went to go and do it, but that machine wasn't working. So they just looked under a microscope and they were able to do it. But I guess they're very good with their hands.
No, I got the impression that it was aligned pixel to pixel.
Or, well, it doesn't have yet. Not quite at that level, but I suspect it's probably pretty good. But I don't know exactly what the tolerance is. But it doesn't need to be pixel by pixel. Yeah.
Okay.
Great. Thanks very much.